Hello, I welcome you all in this presentation related with the subject validability of metals. In the previous presentation, we have talked about the general properties of the heat treatable low alloy steels and the different types of the heat treatable low alloy steels along with their compositions. We know that the composition of the steel significantly affects the validability because the composition affects the carbon equivalent, especially in steels, and that in turn affects the validability. So, since the heat treatable low alloy steels have the quite good percentage of the carbon, like high carbon in like 0.3 to say 0.48%, while the little amount of the other alloying elements like 0.8 to 1.2% of the chromium, 0.2 to 1.1% of the molybdenum, and in some of the compositions we have like little amount of the vanadium as well, like 0.05 to 0.23% of the vanadium. So, when these alloying elements are present, including the high percentage of the carbon, these presence of such kind of the composition in heat treatable low alloy steels leads to the high carbon equivalent, and we know that the high carbon equivalent reduces the critical cooling rate for required for transformation of austenite into the martensite. So, since the during the welding frequently we experience the high cooling rates in the weld metal as well as in the heat affected zone, and therefore, in heat treatable low alloy steels it is very common that whatever austenite is formed during the welding of the heat treatable low alloy steels, these will be leading to the formation of the martensite both in the weld metal and the heat affected zone. Since the martensite formation leads to the significant increase in the hardness, residual stress development in the weld, and increased embrittling tendency. So, if there is a hydrogen in the weldment, then it frequently promotes the hydrogen induced cracking. So, as far as the welding metallurgy is concerned of the heat treatable low alloy steel, the main concern about the like the welding metallurgy of the heat treatable low alloy steel is related with the like the transformation of austenite into the martensite, increased the residual stress development, increased hardness, and in presence of the residual stress development and increased hardness, there is increased tendency for cracking. So, we are mainly concerned here with the control of cracking. So, to control the cracking in case of the heat treatable low alloy steel weld joints, the main we work on the various approaches, like somehow if we can reduce the martensite formation, and if it can be replaced with the softer phases like benite or the pearlite and the ferrite. So, if such kind of the phases can be formed which will be offering us the lower hardness, since these transformations will be taking place at a higher temperature. So, the tendency for the residual stress formation is also reduced in the weldment. At the same time, high temperature transformations will allow the escaping of the hydrogen easily from the weld as well as heat affected zone, and these factors in combination will be reducing the cracking tendency. So, the key here is to have the softer phases formation, so that the hardness can be reduced, residual stress tendency, residual stress magnitude can be reduced, and escaping of the hydrogen can be facilitated. There is one simple step for Realizing this situation in the heat treatable low alloy steel welding is the use of the suitable preheat temperature. We know that increase in preheat temperature will be reducing the cooling rate being experienced by the weld metal as well as the heat affected zone, so that this kind of the favorable conditions can be facilitated. It is very common that 600 degree Fahrenheit preheat if used during the welding of the heat treatable low alloy steels, then it will promote the formation of the bainite, it will reduce the hardness, it will reduce the residual stress formation, and so these factors in combination will be reducing the cracking tendency. But working or means welding of the heat treatable low alloy steels using preheat of a higher temperature makes the welding job difficult for the operators, because now operator will be dealing with the heated steel plates or the tubes or the structures for welding, and so it is not really good, or it is not always appreciated to use very high preheat temperature, because it makes the job of the welder difficult. So, it is important that the preheat temperature is selected suitably, so that the plates can be welded as at the same time the ease of the welding, like the cracking tendency is also reduced, while there is ease of welding for the operator as well. So, while choosing the preheat temperature, certain points are kept in mind, like composition. Higher the carbon equivalent in general will be going with the higher preheat temperature. Then thickness of the section or the restrained conditions under which the welding will be performed. So, lower thicknesses, lesser strain will help us in reducing the kind of preheat to be which can be used. Further, if we use the low hydrogen procedure means the welding process is such that the hydrogen in the weld metal and the heat affected zone will be less, or the welding consumables are used in such a way, the cleaning of the surface of the plates is done in such a way that the hydrogen content, the possibility for incorporation or inducing the hydrogen in the weld as well as the heat affected zone, that is reduced. So, if we are following the low hydrogen procedures, then our requirement for preheat is also reduced. So, that will allow us to use the lower preheat temperature and the lower interpass temperature. It is always desired that whatever preheat temperature is used, the interpass temperature, similar interpass temperature is also maintained for uniformity of the structure at the different layers, so that the all zones during the welding in multi-pass welding will be experiencing similar kind of the metallurgical transformation. Now, we have the way by which preheat is selected so that the martensitic transformation and the cracking tendency is avoided and martensitic transformation is avoided. There are various grades of the heat treatable low alloy steels, and this is one of the most commonly used grade, like 4140 is also there, 4340 is there. These are some of the grades which are extensively used. So, like say 4340 grade of the heat treatable low alloy steels has significantly higher percentage of the carbon, 0.38 to 0.43. So, roughly like 0.4% carbon. Chromium is also like it is 0.8% on an average, and 0.25% molybdenum, and nickel is also like 1.65 to 2%. So, high concentration of these alloying elements in like say this typical grade of the steel will be leading to the higher carbon equivalent. So, increased tendency for the martensitic transformation. As I have said, what different phases will be formed during the cooling of the austenite to the room temperature, that will depend upon the cooling rate being experienced. If the cooling rates are high, then we will be having the complete austenite to martensitic transformation. If it is somewhat lower than like this, then we will be having the phases like martensite and bainite mixture. If further lower cooling rates using the higher preheat temperature is realized, then we will have the phases like ferrite, martensite and the bainite. Further lower cooling rates will allow us to have the martensite, ferrite, perlite, bainite in this typical 4340 grade steel, which is like this is continuous cooling diagram for 4340, which is indicating that how the cooling rate can change the kind of phases which will be formed. So, higher the preheat temperature, lower will be the cooling rate, and accordingly the softer phases will be formed. If the cooling rates are high, only martensite, otherwise martensite plus bainite, martensite, ferrite, bainite, martensite, ferrite, perlite, bainite, and too low cooling rates will be leading to the ferrite and the perlite only. So, these phases will be determining the hardness, and the temperature at which these transformations are taking place will be determining the kind of the possibility for escaping of the hydrogen, will be reducing the residual stresses. Higher the transformation temperature, lower will be the residual stresses that will be induced. So, especially if the martensitic transformation is avoided. So, it is always good to have the suitable cooling rates, so that we can have some soft phase formation in the weld as well as heat affected zone, so that the cracking tendency and the embrittlement tendency of the weld joint can be avoided. As I have said, these are the factors which we need to see while taking decision about the kind of preheat to be used. So, like say for the different grades of the heat treatable alloy steels, and for different thicknesses in inch, which we know that the higher is the thickness, greater will be the preheat temperature that we need to use, changing from 50 to 250. And likewise, if we see increasing the carbon equivalent will be leading to the use of the higher preheat and interpass temperatures. So, greater the thickness, greater the preheat temperature, greater the carbon equivalent, higher will be the preheat temperature. So, this is how we can choose from, and we know that the kind of cooling rates, the kind of the preheat temperature we have chosen, that will be dictating the cooling rate, and accordingly we will be having the martensite, the bainite, perlite, ferrite in the weld joint. So, especially if the weld joints are having like the martensite and the bainite, then subsequent post weld heat treatment becomes important for the two purposes. One is to relieve the residual stresses if these have been developed in the weld joint, and the second is to induce suitable value of the toughness and ductility in the weld joint. So, this post weld heat treatment, like if we see this one where tempering is performed of the weld joints, then increase of the tempering temperature simply reduces the tensile strength of the different grades of the HTLA steels. On the other hand, there is a continuous improvement in the ductility. So, in general, the strength with the increase of tempering temperature, strength decreases, percentage elongation, and the toughness in general improves with the increase of the tempering temperature. Now, if we see here like how the preheat temperature is selected, and what if the post weld heat treatment is possible immediately after the welding, and the situations where it is not possible. So, like the one case we will take up, if the preheat temperature which is possible and being used is preheat temperature is greater than about the 50 degree Fahrenheit above the martensite start transformation temperature, then we know that since this is above the martensite transformation start temperature, so it will be facilitating the complete austenite to the bainite formation. Bainite being comparatively softer than the martensite, it will be reducing the hardness, reducing the residual stresses, reducing the hydrogen content in the weld metal. So, it will be simply decreasing the cracking tendency. So, this is one thing that if possible, then use the preheat temperature greater than 50 degree Fahrenheit above the MS temperature, that is the martensite start temperature. And if this is not possible, like the preheat temperature is less than MS temperature, so in any case the preheat temperature is here. So, the preheat, if the preheat temperature is less, then certainly some of the amount of the austenite will be transforming into the martensite. That will depend upon what is the value of preheat. Like if the preheat temperature is below MF temperature, then complete austenite to martensite transformation will be taking place, and if the preheat temperature is between the MS and MF temperatures, then there will be partial transformation of austenite to the martensite, and this kind of the transformation will be having the tendency for embrittlement or increased cracking tendency. So, in this situation we do not allow the cooling directly up to the room temperature, but we can do the two things. One is, if possible, allow the residual stress relieving, like stress relieving heat treatment, so that the stresses induced in the weld joint can be eliminated and the cracking tendency is reduced. So, if this is possible, then we will perform the stress relieving heat treatment. Means this is the situation where immediately stress relieving heat treatment is possible, then will not allow it to cool it down to the room temperature, but stress relieving treatment will be performed, so that the joint can sustain the period of the handling from the welding to the post weld heat treatment. Otherwise, the weld joint may get cracked immediately. So, if the preheat temperature is less than the martensite transformation temperature, then immediately it is required that immediately stress relieving temperature is performed. Now we will see the situations when the post weld heat treatment. So, now we have to see how about the welding of the heat treatable low alloy steels. Most of the arc welding processes like SMAW, GMAW, GTAW, SAW, and like electron beam welding process, and in the resistance welding process like flash, butt welding, spot welding, all these processes can be used, but we need to see that the development of the cracks, means unnecessary cracking of the weld joints is avoided through the use of the suitable preheat and the controlled post weld heat treatments, so that unnecessary residual stress development and embrittlement of the weld joints due to the high cooling rates can be avoided. As far as the post weld heat treatment of the heat treatable low alloy steel weld joint is concerned, there are two situations when immediate post weld heat treatment is possible, and the second situation is PWHT is possible, and when it is not possible. So, when it is not possible, in this situation what we do, as soon as the weld is completed, the joint is temperature of the weld joint is increased about 50 degree Fahrenheit above the MS temperature, and then it is held at about 1 hour per inch thickness, so that complete austenite to the martensitic bainite formation can be facilitated in order to avoid the cracking tendency, and thereafter it can be cooled down to the room temperature. So, this is one case when immediately PWHT is not possible. So, the whatever the weld joint was preheated will provide further heat for increasing the temperature about 50 degrees Fahrenheit above the MS temperature, and then it will be held for 1 hour per unit per inch thickness, and this will help to facilitate the austenite to bainite formation, which will in turn will reduce the hardness, will increase the hydrogen diffusion, as well as it will reduce the cracking tendency. The another situation when immediate post weld heat treatment is possible. In that case, what we do is will allow the weld joint to cool down below the MF temperature, so that complete austenite to martensitic transformation is realized, and thereafter the weld joint is heated immediately at 1100 degree Fahrenheit to 1250 degree Fahrenheit for 1 hour per inch, and this will be leading to the reducing the residual stresses, will be helping to form the softer phases, and thereafter we can allow it to cool it down to the cooling to the room temperature. So, these are the two kinds of the situations. In one case, when immediate post weld heat treatment is not possible, then after the completion of the weld joint is heated above the MF temperature up to 50 degrees centigrade, and the second case, if the PWHT is possible, then we will allow the complete martensitic transformation by cooling down below the MF temperature, and then heating at this temperature for 1 hour will help to form the softer phases and relieve the residual stresses. Now, we will start the another important aspect, that is about the chromium molybdenum steels. So, in case of the chromium molybdenum steels, for various high temperature, the components which are used at a high temperature, especially in thermal power plants and a number of the chemical industries and like petrochemical industry and the food processing industries, where the components made of the steels are required to work at higher temperature, which may range like say 300 to even 650 degrees centigrade. So, in thermal power plants it is common like 500 to 650 degrees centigrade, even nowadays 700 degrees centigrade temperatures are also used. So, so the weld joints, whatever the weld joints are needed to give the desired size and shape to the various components used in these thermal power plants, they must survive at a higher temperature like in the range of 500 to 650 degrees centigrade. And so, we try to choose the steels which offer the significant high strength at elevated temperature, and they show group creep resistance. So, there is no change in dimensions as a function of time when the component is used at a higher temperature. So, high temperature is strength and the good creep resistance, these are the two important requirements for the components to be used at a higher temperature. So, in this regard, the chromium molybdenum steel is one of the most commonly used heat resistant steel which is used for these applications. So, in these chromium molybdenum steel we have the carbon, normally it is very low like 0.1 to 0.25%, and the chromium in chromium molybdenum steel really dominates. It can range from 0.5 to 9%, while molybdenum generally is found in the range of like 0.5 to 2.25%, but more commonly it is 0.5 to 1% only. Apart from this, nowadays even tungsten is also used in improved grades of the steels. Niobium is also used so that their not just high temperature strength, but also the creep resistance can be enhanced. Here each element plays a very specific role, like chromium offers the resistance to the oxidation resistance, and then sulfide corrosion resistance is also offered by the chromium, and it also helps in increasing the high temperature strength of the steel, high temperature strength of steel. So, these are the three important roles which are performed. On the other hand, when molybdenum is used, it primarily helps in increasing the high temperature strength of steel. The similar kind of the role is also performed by the tungsten and the niobium. When these elements are present, they will form, because of their good affinity with the carbon, they tend to form their carbides like molybdenum, niobium, chromium, etc. So, some of these carbides are good because they are stable and they do not decompose even at elevated temperature, and that is why they help in imparting the good resistance to the creep as well as the high temperature strength. These steels are used in different conditions, like these can be annealed and tempered or quenched and tempered condition, or the normalized and the tempered conditions, and these offer quite good strength and the ductility. So, now we will see the most common grades of the chromium molybdenum steel, like the 0.25 chromium, 0.25 molybdenum. This is the kind of composition having the range of the chromium 0.5 to the first grade is like 0.5 chromium, 0.5 molybdenum, and having the chromium in the range of 0.5 to 0.8 and the molybdenum 0.45 to 0.65. Likewise, there are different grades. The one of the grade is like 9 chromium 1 molybdenum having 1.15 carbon, and then we have the chromium in range of 8 to 9%, 8 to 10%, and the molybdenum is 0.9 to 1%. So, and while these the single values shows the maximum possible content of that particular element. So, here in these grades maximum content of the carbon is like say 0.15%. Wherever the range is given, the range will show the kind of the allowable range for that particular value, like the maximum allowed value of the sulfur and phosphorus. These are the values like 0.03 or 0.045% in order to avoid the kind of solidification cracking tendency of the weld joints. Since as I have said, these steels are used at a higher temperature and they offer quite good ductility and very good strength. So, in the as per the form of the steel, we have a very wide range. So, here like say these chromium molybdenum steels having the ultimate strength in the range of like say 60 to 115 KSI, and in case of the yield strength it is 30 to 100, elongation is 13 to 18 percent. So, these are like quite good combination of these have the quite good combination of the strength and ductility. Now, I will summarize this presentation. In this presentation, basically I have talked about the welding metallurgy of the heat treatable low alloy steels and the way by which we choose the preheat and the post weld heat treatment conditions for the heat treatable low alloy steel weld joints. And I have also talked about composition and the general properties of the chromium molybdenum steel. Thank you for your attention.